It's my pleasure to have Robert Raussendorf visiting us from UBC. Robert did his PhD in Innsbruck with Hans Briegel and invented so-called measurement-based quantum computing at the time. He then went on to the Perimeter Institute, where in an effort to figure out how to make measurement-based computers fault-tolerant, he invented surface codes, which have essentially revolutionized computer architecture for quantum information. And now he's been at UBC for, what, 5 years?
Yes, about 5 years.
And will tell us about some of the neat stuff he's doing there. And as a reminder, at 4 o'clock over in the CSS building, we'll have tea and cookies with the speaker.
Jay, thank you very much. Very nice introduction. And let me just make one correction here. I cannot claim the surface codes. The surface codes, they were invented by Alexei Kitaev, and I just took them and made a scheme of quantum computation out of it. And went beyond the memory. All right, I thank you for showing up and filling this room. I'm very happy to speak in front of such a large audience, although I learned that the Chinese food apparently helped. All right, I'm coming to a physics place, so I try to be as physicsy as possible. I am a physicist by training, but I have moved a little bit into, I have done quantum information, and I may have moved a little bit towards the computer science side of it, although it's not quite computer science proper either. So I try to be as physicsy as possible, so I have chosen to talk about computational phases of quantum matter. So the question that I will be dealing with today is, what is the computational power of quantum states? Yeah, and then if, say, nearby states in Hilbert space have the same computational power, that's something to be proven, but let's assume for a moment it was like that, then I can talk about computational phases of quantum matter. And yeah, I want to map out a phase diagram for these computational phases. This is the goal for this talk, but I will not nearly get there. Sort of, we know very, very little about this phase diagram at the moment. So I will review for you a few things that we know, but by and large.
Now, can we have some light again? It helps taking notes.
So by and large, this phase diagram is unknown. So this is the question really that I want to talk about, and here you have an outline. So first, we need to make sense of that question. We ask, so what does computational power of quantum states even mean? And quantum computation by measurement is, as we shall see, a way of making sense of this question, and this will represent a framework in which I analyze my question. I will briefly talk about entanglement. Entanglement is the most usual suspect for the cause of the quantum speedup. And in this scheme of quantum computation, it's particularly suggestive. But actually, if you give the question a little bit more scrutiny, the phenomenology is rather twisted. It's not as simple as that. And I want to go a little bit into it. I want to give you a very intuitive result of the role of entanglement in quantum computation and a very counterintuitive example. Okay, and then we are talking about specific quantum states, physical quantum states, and their computational power, and then I summarize.
You'll tell us what AKLT stands for?
Oh yeah, yes. Okay, so yes, I will do it in the talk, and since you asked me, I can do it right now. AKLT stands for the four names: Affleck, Lieb, Tasaki. Did I forget anybody? Affleck, Kennedy, Lieb, and Tasaki. And what is this? It is a specific. Let's talk about the spin chain. I will later be talking about the two-dimensional case, but let's talk about the one-dimensional case for a moment. So the one-dimensional case would have to do with spin 1. So what the AKLT model is, it is a solvable model for a rotationally invariant spin system. So that is very of great interest to condensed matter physicists. They want to figure out properties of spin systems. They want to know what the ground state is. They want to know whether there's an energy gap, a finite energy gap above the ground state, and things like it. So a model that condensed matter physicists really like to solve would be the Heisenberg model. Well, that's you're nodding. Is this something that you do?
Well, about 40 years ago.
I see. All right. And so the AKLT model has a Hamiltonian that is very similar to the Heisenberg Hamiltonian. It's not exactly the Heisenberg Hamiltonian, but this correction makes it an analytically solvable model. So that is an instance where you have SU2 symmetry, rotational symmetry of the spin, and you can actually solve the model. So let me write down what the Hamiltonian is. So this is spin 1, and the Hamiltonian is sum over all nearest neighbor spins, Si times Si plus 1. So these are all operators. So that would be, well, let's have a coupling here in front. So that would be Heisenberg so far. And then we have an extra term. Yeah. Okay, and so this correction actually makes this whole model solvable. So we know exactly the properties of that spin chain. We know what the ground state looks like, and we know that there is a gap above the ground state. And later in my talk, when I come to talk about all that stuff, I will write this Hamiltonian in a different fashion. And that's the main property that you get something out of. So what this interaction term here really is, it is the projection onto the spin 2 subspace. So on nearest neighboring sites. I don't know if I'm writing this very well. So we are projecting on the spin 2 subspace. So look, we're having spins 1 here, so each pair of neighboring spins, they can combine to spin 0, 1, and 2. And what this for Hamiltonian really is the projection onto the spin 2 subspace. And that is the essential property that helps us write down what the ground state is. So that's a thing we will be talking about. And why? Okay, why we are going to talk about it, maybe you'll see as we move along. But that's one of the results I want to present in my talk. All right, so here we go. That's our outline. So let us begin. Let us begin with the question of how does the question of computational power of quantum states even make sense? I mean, okay, so there's a quantum state sitting here that doesn't do any computation per se. So if I want to compute with the state, I need to supplement the states with operations by which I communicate with that state. But in such a scenario, well, we must make sure that the operations by themselves don't have a lot of computational power. Because then, if they had a lot of power, then the power of the scheme would not be attributed to the state, but rather to those operations. So we will supplement the state by very simple operations. So in quantum mechanics, what can these operations be? They can be unitary operations in measurement. In addition, we allow classical communication, very simple processes.
So I can substitute operation for gates?
Yes, you can do that. And really, I'm talking about unitaries and projective measurements here. So, and we will invoke an organizing principle. I mean, that's a choice that I'm making. You could invoke other organizing principles, but I am classifying those unitaries and measurements according to their locality, by which I mean we have here a bunch of physical systems, and each of those unitaries, I'm asking on how many of those systems will they act. So they can be one local, meaning they act only on one system. They can be two local, that is, they act on two systems at a time, three local, and so on and so forth. So this is my organizing principle for these unitaries and measurements, and this gives me the following infinite table. I can now study, for this schema of computation, for potentially extracting computational outcome from my quantum states in this fashion. So I may restrict my operations to be strictly local, 2 local, 3 local, 4 local, and then I may consider computing with unitaries only, unitaries and measurements only. So this gives me this playing field here. And now we want to kind of restrict to something simple. So first we observe, well, if I have unitaries only, I can never read out a classical result. So we can scratch out this whole line here, this infinite row in the table. Then we can scratch out even more. And this actually requires proofs. This is not a trivial result that requires a proof. Let me just state those results. I can further remove all this portion of the table. And the reason for that is, as soon as I have 2 local operations, they become so powerful that I can compute with them alone. I do not need any particular quantum state to begin with. Those operations will do it by themselves. So in that case, talking about computational power of quantum states doesn't really make sense, because the operations by themselves are so powerful. So I can scratch out all this infinite portion of the table, and now I'm down to 2 fields. Just unitaries and measurement, or measurement alone, one local. So we don't know yet what the computational power of that scheme is. It turns out, in fact, the unitaries don't help you, so you're down to that field. So we do not know what but from our infinite table, we are down to one setting. We are looking at quantum computation using quantum states and local measurements. And we are asking, all right, is there any computational power? Okay, and the answer to that is yes. Even in this corner of our table here, in this scenario, you can do universal quantum computation. And yes?
So in the sector that you've labeled computational power independent of state, do you mean that you get computational power whether or not the state is specially prepared, or that the degree of power is independent of how the state is prepared?
You get universal quantum, the former. You get universal quantum computation, and you don't need a state to begin with.
Yeah, but you could well imagine that with the right state it would work better.
Yes, but but without a state, it already works so good that it's hard to find a significance in better.
Okay.
I mean, you are, even without a state, in this green area of the table, you are already efficient.
You need to know what state it is, though, right?
You mean here in this region?
Yeah.
No, I mean, if you have measurements, you just measure local states, and then you take what you get.
But if it's universal, does that mean I've lost any classificational ability?
Universal, oh yeah, sorry, but thank you for that question. Universal in our sense is computationally universal. That's different from universality, say, in statistical mechanics. So what we call universal is that you can compute everything that a quantum computer can possibly compute. Yeah?
Of that size.
Of that size, yes. So if you have say in that corner, if you have a family of states where the states in the family get bigger and bigger, then, and that's a universal family, then you can compute everything.
But if I want to classify the quantum states, which I thought was one of your aims, then I seem to conclude that that criterion gives me no classification. I mean, if they're all quantum computational universal.
Sorry, I hope I get you right. The computational power here in this field will depend on the state. So the simplest example, take a product state. You have local measurement, product state, everything is local, no computational power. But it turns out, and that requires a proof, there are quantum states that give you universal computational power. And there will be things in between, and I will talk about this. All right, so let us now talk about this computational scheme that's represented by this question mark in the left bottom corner. So, I mean, this would be a talk in itself that I would have given a long time ago. I just want to say that this scheme exists, and I would like to treat it as a black box for this talk. I do not have the time to explain what's going on. And let me just say that the following actually works. You can prepare a quantum state of a suitable kind, a so-called cluster state, which is a specific entangled state on a bunch of qubits on a two-dimensional lattice, for example. So you prepare the state and put it in place, and then you begin measuring those individual qubits in the state. And this gives you universal quantum computation. In a measurement, you can always choose the basis but never the outcome, but choosing the basis is actually enough to tell the state what quantum algorithm to implement. You can implement everything on that if you choose the right state. And I will, in a few slides, I will give you one choice of a good state, and this also allows me to make a physics connection with cold atoms and optical lattices. Okay? So, but the scheme is this: you put the state in place, and then you begin to measure locally, and in this fashion, a quantum circuit is imprinted on that state, and you obtain your computational output from the measurements that you get on that state. All right, this is as I said, to justify these claims, that would be a talk by itself. I do not want to go into it. Please treat it as a black box, but that is the framework in which I will be discussing things here in this talk. So yes, this is the first thing. There are universal resources, I mean quantum states that give me universal computational power. And also, and that's a result that I would like to tell you a little bit about today, there's actually quantum states that are ground states of somewhat physical Hamiltonians that give you this universal computational power. So I mean, the step from here to here is asking the question, okay, so we now know that universal resource states exist. What about states that appear in nature, that naturally occur in nature? And well, this state maybe is sort of a state naturally occurring in nature. Maybe you can get it in optical lattices. It's not so, I mean, it's not so straightforward. Yes, we know in one dimension these states really occur in nature. I guess 2D is more tricky. Good. So let me just say one more thing about the cluster states. I will not give you a formal definition today. I just want to show you that you can efficiently create them by unitary evolution under the Ising interaction. Good, so much about them, and here you have a bunch of examples. So the Bell state is one, the GHZ state is a cluster state, and here the code word of the Steen code is also a cluster state for this funny interaction graph. Let me say something that's probably more familiar to you here. Let me briefly make a comment about cold atoms and optical lattices. This was actually our starting point way back to begin this investigation. So this was at the time when Bloch and Greiner did their experiments with cold atoms and optical lattices. I mean, they could drive the superfluid to mod phase transition. And what we were thinking about is, all right, you have atoms trapped in an optical lattice, one atom in each well, and then it was known that one could make those atoms well, I should say they would form qubits. There would be two hyperfine states that would give us a logical states of a qubit. And now it was known that by playing with the polarizations of the laser beams that would make that lattice, one could have state-dependent transport in these optical lattices. That is, one could send the atoms on a journey depending on the state that they were in. And so one could make them visit each other and scatter off each other. This would mediate an interaction. And it turned out that if you look at it more carefully, what this is just an easing interaction. So you can have the atoms acquiring these state-dependent phases, and this happens simultaneously on all sides. And then you're asking yourself, so you're getting certain states, are they good for anything? And this was the starting point really to think about cluster states. You get cluster states if you adjust this interaction phase to pi. All right, so just to make I think probably some of you here in this room work on optical lattices and called atoms. I think that might be the case, so I just wanted to point out this connection. Good. All right, I think I'm done with this measurement-based scheme of computation. Oh, now there's one more thing. So there's one thing that I want to point out here. I wonder if you have wondered about this. I mean, how could this ever lead to deterministic computation? I mean, the problem is when you do a measurement in quantum mechanics, the outcome is completely random. So you end up with a bunch of random outcomes. I mean, how can that give rise to computation? And the reason is what we're reading out is not individual measurement results. What we're reading out in the end, or what we're outputting, is correlations about these measurement outcomes. And even if the individual outcomes are random, they may be strongly correlated. Yeah? All right, and for the physicists, so the correlations that we are interested in here for this computational scheme, they are not two-body, three-body, four-body correlations. What we're interested in is really the correlations that have a large support. I mean, that have a support that's as big as our system. We are really interested in those very highly non-local correlations. All right, are there any questions at this point? Yes?
So you measure correlation.
Sorry, I couldn't quite hear you.
You say you measure the correlation.
Yeah.
Do you have to do it one time or not?
You have to do it once. So that would not give you good statistics. So I mean, you could not get a good handle on the expectation value of that correlation. Yeah. But for quantum computation, this is actually good enough. I mean, if this quantum computation tells you something, I mean, a particular value should be highly probable. And how probable it is, you don't need to know for the purpose of computation. You just want to get it sufficiently often. There was a question here.
So if you do this operation where you shift things in a state-dependent way and then do a pi phase shift, and then you get this cluster state.
Yeah.
And this is very powerful, and it has these long-range correlations that you want. What if the phase shift is something different? Do you still get a state that has computational power but less, or?
Well, I cannot give you a definite answer on that question. Just out of my guts, around this phase of pi, I mean, there's definitely, I mean, that's for sure. Around this phase of pi, there's definitely a region where you retain the computational power. This is simply by fault tolerance of quantum computation. I would think that as you move away, your life gets difficult. I think there's really, this point is really, this point of pi and the little phase around it is special. But that's just out of my guts. I would think if you're away from pi, probably everything is getting a lot harder, and probably you do not get those long-range, very strict correlation, high order strict correlations that you need to compute. I think you wouldn't get them. I think this phase of pi is special, but it's just a gut feeling. I cannot prove it to you.
So some level of fault tolerance is crucial to your definition of computation, is that right?
No, it is not crucial to my definition. No, I would not say that. I'm just saying fault tolerance often allows me to make the following point. If I have in my hypothetical phase diagram that I'm trying to construct, if I have a point of computational universality, then on some hyperplane of whatever dimension, I have a ball around it where I have the same computational power. So maybe that is, this fault tolerance argument helps me to argue that there are computational phases with an extension. Does it make sense?
Yes, except that when you said they're random, but then they're long-range correlations. I mean, that's a little different from the Turing view of computation, where if I think of, doing number theory, then the answer is an integer or not. Mm-hmm. And there's no question of fault tolerance there. I mean, admit if I want to solve a PDA or something like that, I have to discretize and so on.
Yeah.
But it seemed to me that when you were saying it's random, but I'm interested in long-range correlations, I have to accept some degree of tolerance there for my definition to be workable.
No, these are distinct. I can say no. But now let me try to illustrate it to you. So maybe I should have said this. The way you prove the universality of the scheme is by mapping to the circuit model. And, which you can do. And the fact, you need to work a little bit, but the fact that all these measurement outcomes are random and in fact completely random does not affect the computation. So if the circuit model is fully deterministic, which it normally isn't, but if it was, then this simulation of the circuit would also be fully deterministic. So you can kind of, how should I say, so this randomness does not affect the logical processing.
But randomness may affect the length of the computation, the amount of resources you need.
Say it again?
May affect the amount of resources you need, how far out you get. Your measurement outcome can determine that you need to go longer to get where you need to go.
No, not here.
Not here.
Not here. I mean, in other schemes of classical site processing, yes, but not here. So the size of the computation is fixed at the beginning. And you can kind of play your little tricks with those measurement outcomes and just look at those correlations. It's actually technically a little bit tricky, and I would like to take the discussion offline. I can tell you much more about it, but let me just, maybe if that helps, give you an analog with Bell states. I mean, we know that if we have a Bell state, spin singlet, we can measure this spin in any direction that we like, and we can measure this spin in the same direction. We know those spins will be anti-correlated. So that is not really, there's no input and output, it's not a computation, but it is, I have the same effect that individually those outcomes are completely random, but then if I look at their correlation, it's deterministic. And it is that type of thing that I'm exploiting here.
Thanks, that's very clarifying, very helpful.
Okay, so it's an hour, right? Good. Is that, am I wrong? It is, okay, okay, good. So let's move on here. So that was kind of my preparation, and now let's get going with the talk. So this is what I want to talk about. So as I said, my goal is to map out this phase diagram, but I cannot show it to you. It is indeed very, very little known about that phase diagram. So what we know is only by pointing our flashlight in certain directions, and then we find a bit of funny phenomenology. And I want to talk about these funny bits of phenomenology. So, universal resource states exist. That's what we just discussed. Then AKLT states were at least mentioned, and this is one of the results that I want to show to you, that they are also universal. Then more talking about computational phases, actually this computational of power extends into phase. That's what I want to talk about. Surface codes, maybe a little bit if we have time for that. Yeah, so this is the particular, specific results that we know. On the other hand, what general statements can we make? And there is a few general statements that we can make about the role of entanglement in this scheme of computation. And this is what I would like to begin with. All right, so intuitively, it seems that entanglement should really be the cause for the quantum speedup in the scheme, or everything should be governed, the computational power should be governed by entanglement. At least that's what intuition would tell you, and the reason is the following. So we start with an entangled state, and then the way we process it is by local operations, local measurements and classical communication. So by definition, by the very definition of entanglement, it decreases over the course of computation. So I start out with entanglement, and I end up with no entanglement, but in return, I get a computational outcome. So that seems reasonable to assume that entanglement is really the cause for the quantum speedup here in this scheme. We're burning up entanglement to get a computational outcome. So now, let's see, can this intuition be made rigorous? And yes, it can. So there is a theorem due to Martin van den Nest, and it says, so what it discusses is the computational hardness of classically simulating such a measurement-based computation. And what he finds with his collaborators is that the cost of the classical simulation is polynomially, it's polynomial in the size of the state, but it is exponential in the entanglement contained in that state. So this means I must have sizable entanglement, otherwise I cannot have computational power. Otherwise, if entanglement is small, the classical simulation cost is low, and there's not much computational power in the scheme. Yeah. The LaTeX has this amazing ability, even in the slide environment, to put in footnotes. So let's put a footnote here. I just said the simulation cost is exponential in the entanglement. Yeah, this is exactly what you want to hear. This is exactly what's confirming the intuition, but really such statements crucially depend on the entanglement measure that you're using. So here's where things are beginning to get hairy. So people were just paying attention to the simplified message, but actually it comes out more and more and more that such statements do not hold generally for entanglement, but they often specifically refer to one particular entanglement measure, and you cannot obtain them for another. Yeah. But anyway, so this is the confirmation of the intuition. It's the result that confirms the intuition. Now, is entanglement sufficient? No, it is not. You can have lots of entanglement, but no computational speedup, and you can convince yourself of this in a number of ways. But it's actually even worse than that, and that's the reason I choose to show this result. It is even such that entanglement, too much entanglement, can actually be detrimental to quantum computation. So the more the worse. This is a very counterintuitive result, but it is actually, and again the same footnote here, with respect to a particular entanglement measure. So
which is a different one than the one.
It's a different one than the one before. Yes.
So these ones are width, small width, is what you're going to say.
Well, let's see. Actually, in terms of width, I don't know. I have not analyzed them in terms of width. I can't make a statement about it. But anyway, let me go through the argument, because the argument is actually super simple. It's a proof that you can do in a talk like this. It is a very short proof, so let me do it. So actually, what we're going to show is that if the resource states are very highly entangled with respect to that measure, you can perform the computation simply by coin flipping. And well, that's a cheap thing to do. Or, yeah. All right, so let's I think, yeah, even now we have the time to go through this result because it's just very short. So let me start out by defining the entanglement measure that we're using. I will not show you that it is an entanglement measure, that it has all the properties you need for an entanglement measure, but you can look that up. So here is a definition of what it is. So here's a quantum state, psi living somewhere in Hilbert space, and you want to compute its geometric measure of entanglement. So what you do is you look at the product state that is closest to it, by which I mean has the largest overlap with it. Then you take this overlap, more accurately, the absolute value of the overlap squared, and take its logarithm with a minus sign in front. And again, you optimize this over all product states here, and this gives you this measure of entanglement. Okay, so it's just the definition. An immediate consequence is that this entanglement for qubits, this entanglement measure is bounded from above by n. So you cannot have more than n bits of entanglement in n-qubit quantum states. And just maybe to help you a little bit to see this, it is a direct consequence of this definition up here. So let's assume the entanglement for some state was larger than that. Then this means the probability of this measurement outcome occurring would be smaller than 2 to the minus n, but then we can extend that given state to a basis, and then all these other measurement outcomes must be even less likely, but there's only 2 to the n of them because we're dealing with an n-qubit system. So that, but I would, I have to sum up these measurement outcomes, and they have to give 1. And they couldn't if that measure here was larger than n. I don't know if that makes sense. But it's a homework problem for you to do. If my explanation wasn't good enough, it's a simple exercise for you to show that this is smaller than n, smaller or equal to n. I hope that's roughly all right. Okay, and now, so with this property, we can now do the proof. So let us look at this setting. So we have an n-qubit quantum state. There is 2 to the n possible outcome configurations for local measurements. And we divide them into 2 fractions. There's the good fraction, in which the computation succeeds, and there is a bad fraction in which it fails. And I make no assumptions whatsoever about the processing here. I mean, I'm just saying, if I get those measurement outcomes, then I can do my stuff and get the right answer for this computational problem, and here I fail. So now we are invoking just 2 assumptions. Namely, that the entanglement, the geometric entanglement of the state we are starting with, is almost maximal. So it is n minus a little bit delta. Yes?
So what actually does it mean to succeed and to fail?
Yeah, so suppose you, so quantum computations are usually probabilistic. So think of Shor's algorithm. We know that in the large size limit, Shor's algorithm has a success probability of 1 over 600. So you have your number, which you know is a product of 2 primes, and then you do this thing, and you learn the prime factors. And then you check it, whether they actually, when you multiply them, give you the number you started with. So in a quantum algorithm, this test may actually result in failure. So the numbers you got were not right. Because that's what it means. Your success probability is only 1 over 600. So you do it 600 times, and then you have a good chance of succeeding. So what I want to illustrate, what I wanted to illustrate here was quantum algorithms can fail. They are, but then quantum algorithms often solve problems for which a solution is hard to find but easy to check. So that doesn't matter. So you do it just over and over again. And yeah, so this is what it means for a computation to fail. Just outputs nonsense. And that would then be easy for you to check. Yeah? Yeah? And in such a case, you start over. Okay, so this is what it means to have a bad fraction. This is where the computation fails, and this is where the computation succeeds, i.e. it really solves your problem. Okay? Other questions here at this point? Good. Okay, then let's actually do it. So here are the two assumptions. We are saying that the state has close to maximal entanglement, and also we are assuming that this computation succeeds with high probability. So it's, and I mean, we don't need this 1/2 is not critical here because it's just an example. So this is actually, this can be used to compute. You're learning the right answer with high probability. So these are the only assumptions that we are making. So, all right, and now the question that we are asking is, what is the fraction of good outcomes? So the total number of outcomes is 2 to the n, and the good outcomes is where the computation succeeds, and we are asking about this ratio. So, we know, first, that the following identity holds for all measurements outcomes phi of s, in particular for such outcomes in a particular basis. We know by the definition of the entanglement measure, this is smaller than 2 to the minus the entanglement measure. And the reason is that this holds as an equality for the most likely state. This is what this is the very definition of the measure. So this holds as an equality for the most likely state, and then for other states, this must be lower. Okay, so what we now do, and here this the entanglement measure, so this amounts to this, by our assumption that the entanglement was almost maximal. So then, the success probability of the computation, which we assume to be 1/2, is the sum of this probability for an individual outcome over all the good outcomes. Okay? And now we're using this inequality in here, and we find that this success probability is, well, the number of good outcomes times this. Okay? And we see that we have the answer to our question right here. So here we have now this ratio of the size of this set divided by 2 to the n. We just have to move this thing to the other side. And here we go. This ratio is about 1/2, meaning that it is very likely to get a good outcome out of, and so instead of running this computation, I can just flip a coin. And with the probability of 1/2, or almost 1/2, I get a good outcome. So I can simulate this entire computation just by coin flipping. Right? So let me summarize. Why did we go through this argument? Well, to show that entanglement can really be detrimental to the power of quantum computation. Here we have states with close to maximal entanglement, and from the point of quantum computation, they are entirely useless. You could just simulate those computations by coin flipping.
Robert, doesn't that depend on your metric for entanglement? I would consider
Yes,
those
it does.
those states, by some measure, not entangled at all, hardly entangled. Like a big GHZ state, it's hardly entangled, but it has perfect correlations over every qubit.
Yes.
There's only one EBIT of entanglement there.
Yes. Yes, so I totally agree to that. Those, this result depends crucially on the entanglement measure chosen. So that's also a point that I want to emphasize. Kind of entanglement now appears as something fractured. You have those various entanglement measures, but the results that you're able to derive, they pretty much depend on what measure you choose.
But that GHZ entanglement is nevertheless an extremely useful entanglement for certain kinds of things.
That like metrology.
Yeah.
Yeah, for metrology, probably. For computation, not.
A
what is the distinction between a good outcome and the success of the computation?
There is no distinction. Good outcome leads to success of computation.
And the Gross there is David Gross?
Yes, it is a David Gross, but not the one that you think it is.
That's what I wondered. Thanks.
Yes, it's a funny coincidence, yeah. No, it's not him, not that guy.
William.
Well, it didn't quite seem the style. But
yeah, all right. Actually, yeah, so I'm running out of time, so let's just skip the surface code stuff here. It's just to show you that there is various phases, really. So the product states are obviously trivial. These guys are universal. Then you can think of other states which have to do with the surface codes that came up in Jake's introduction to my talk. And their computational power is different. It's the computational power of Majorana fermions, which turns out to be not a lot. But let us not go through that stuff. Let's give
No, but I mean, that's crucial for the phase diagram and the classification.
Yes, I just wanted to make this, so there is, I just want to say there is more phases.
Yeah.
So, I mean, more points of interest.
Yeah.
I haven't talked about phases yet. So what I want to do is I want to talk about one more point in that phase diagram, and then actually, in the end, very end, talk about phases, something of a given extent, which will be related to AKLT. So now we are moving to AKLT, and what motivates this analysis is what quantum states, I mean, useful for the scheme of computation do actually occur in nature. And that could be ground states. I mean, at sufficiently low temperature, I mean, ground state is what you find in nature. So what about them? I mean, among the ground states of sufficiently simple Hamiltonians, are there any states that are useful for the scheme of computation? So that's the question we are asking here. And so that is, I mean, I just want to mention a result that gives kind of a conditional yes to this question. I mean, you would need to ask yourself, what do I mean by a simple Hamiltonian? And the first criterion would be two-body interactions only, I think. And this problem, I mean, finding a complete universal ground state for two-body interaction was solved here by those people. But okay, I mean, the Hamiltonian still takes up half a page if you write it down. So from some...
But is it finite range? I mean, because that's the other thing.
Yeah, it's finite range.
Yeah.
It is nearest neighbor effect.
Okay.
So, okay, and this is the work that we are now building on. We are coming up with a Hamiltonian that is arguably simpler, namely it's the AKLT Hamiltonian on spin 3½ particles in a honeycomb lattice. So the construction is the same like this, except if you were talking about a 1D system, you were using spin 1, here we're using spin 3½, but the construction for the Hamiltonian is the same. It is a projector on the highest possible spin sector. So in the case of the chain it was 2, here it is 3, and just, I mean, I will not use it, but just I would like to show you that actually the spin state isn't, and the ground state of this Hamiltonian is exactly known. Okay, so yeah, so the result here is that this state is universal for quantum computation. And maybe I just go, yeah, no, I will not. I will just give you an outline. I mean, I'd be happy to talk about it. I mean, if you're interested in it, I can show you how you actually prove it, or at least give you a little bit of a more detailed outline, because the argument is quite interesting. It involves percolation theory, it involves numerical simulation to check that you're actually in the percolating phase of the percolation problem. But anyway, what you want to do is you find local measurements. Local measurements is what you have in your repertoire, and convert this state into a cluster state, which you already know is universal. So that's the way of going forward here. And it's actually a somewhat long-winding but interesting proof. let me not go it.
But if I go back to this phase diagram,
Yeah.
there you are, doesn't it just say there's another point in the same phase, in the universal phase?
Yes, but but then so the yeah, but the question is, is there a line between here and here? I can draw such that two neighboring points on the line are similar to each other, and I keep the universality all the time. We haven't shown that, and our method of reduction of this state to this state is very drastic. So we're doing a measurement, and that completely changes the state. It's not a, we're not continuously deforming the state, we're doing something very drastic, and end up with a random analog of this thing. And anyway, so we don't know if there is a continuous line between the two.
So
therefore,
the crucial question is the question mark there as to whether they could be separate phases.
Yeah, so there is, the question mark is there a boundary here, and where does it lie? Yeah. So there is one boundary about which we know a little bit. So this is the final thing the final slide that I have. Although maybe I better, well, no, let me just do it. This is work by an Australian group, and what they have done is they have taken the AKLT Hamiltonian and deformed it in a particular way. So as I said over here, the AKLT Hamiltonian is rotationally invariant, SU2 invariant, so their deformation breaks that symmetry, prefers a particular axis, so you end up with a U1 symmetry. And you can make this this deformation stronger and stronger, and then you can investigate what happens both from the physics point of view. You can ask, okay, what happens to the physical order of the system? And you can ask, what happens to the computational power of the system? Yeah, and it turns out that in both cases there are phase transitions. So as you make the symmetry breaking stronger, there is a point at which you transition from this order, where the AKLT point is in, to so-called Neal order, where spins are, neighboring spins are anti-aligned. Now, with regard to the computational phase transition, it turns out that you are undergoing a transition from universality to no computational power. And the funny thing is that they happen at the same point. So physical phase transition coincides with the computational phase transition. So this is a result that I think justifies for us talking about really extended phases and the phase diagram for the computational power of matter. All right, so this is the, yes, there are questions?
Yeah, go back to the phase diagram, because you don't show where these highly entangled states that are non-universal lie. And is that just because it's a different entanglement measurement? You don't know how to map it back on here?
Yes. So this is about special points. I mean, those results were general results, and the results that I have drawn here deal with special points of interest in the phase diagram. So yes, I do not know at this point how to bring those general phase diagrams in here. Although I can say one thing. I mean, we can ask about the separation of the cluster states from those maximally entangled states. I mean, they are very far away. In terms of this localized entanglement, cluster states have half as much, they are right in the middle between unentangled and maximally entangled. So and that holds
by what measure?
By geometric entanglement. So that was what I was referring to. They lie right in the middle.
What about for entanglement width, which seems to be the thing that gives you power?
I need to think about it. I cannot give you an answer on the top of my head. I can say one thing, but that's not satisfying. It's not going to satisfy you. When we have a grid like that, we know that I mean, Q with F, this is the typical cluster state scenario. We know that the entanglement width is actually the geometrical width of that thing. So that whatever the smaller dimension is, width or height. Yeah, but that doesn't answer your question. How this relates to the maximal entanglement width that you have there. Haven't looked at it. All right, so that is actually this brings me to the conclusion of my talk. So I mean, I hope I have conveyed to you the idea that that the question makes sense. Asking what is the computational power of quantum states. If you take the viewpoint that the question makes sense, you can begin mapping this phase diagram, and we know very, very little about it. We know a few points of interest, and we know a few general results regarding entanglement. Yeah, so everybody is invited to contribute to the phase diagram. Thank you very much for your attention.